Okay, so we are continuing with kinematics in one dimension, but let's just quickly remember what we have done up to now. It's not much. I mean, probably we shouldn't have spent 1 week on this. I think we didn't, but in any case, first we need to have I mean, we are investigating the motion of a particle, a point particle. We're assuming that it's a point particle, but if it is not, then we can somehow handle this by choosing a point. We then choose a reference frame. So that's a choice involved. You can investigate the same motion by choosing a different reference frame. Let's just remember this. Let's see. In that case, we define these kinematic quantities: the position, the displacement, the average velocity, instantaneous velocity, and instantaneous acceleration. So we can also define the average acceleration as well. But the concept of average velocity, I'm just going to use in some places. And so as a result, I'm just going to show it in here, right? So this is essentially the concepts. There's, again, no physical statement in here. Sorry, there is no physical law in here. It's just a mathematical relationships, right? We are defining these concepts of motion. So then we have said that at some point, what if the acceleration is constant? So it's a constant as a number, of course. So if it is negative, it's always negative. Just keep this in mind. So in that case, we have said that the position would then be in that form, x0 plus v0t plus 1/2 of at squared. And if I take the derivative of that expression, first term is just a constant, so its derivative just goes away. Second term gives us v0, and third term gives us at. And if I take one more derivative, it's the derivative of the velocity. In that case, the first term gives 0, and the second term gives a, and whatever. So as a result, we just then end up with this value of the acceleration, which has been constant, right? Probably I should have used a different symbol in here, but in any case, so x0 is the initial position. And v0 is the initial velocity. And 0 is the initial time. All right, let me also say this. I mean, by convention, we just take the initial point to be equal to time being equal to 0. But of course, this changes from problem to problem. But most of the problems, in most of the problems that we are going to solve, this is what we are going to take. All right, all right, so the last one is kind of trivial. Okay, so in any case, there are some other ways of actually dealing and deriving these, and probably these are the ways of derivation that you have seen, but this is using, this uses the concept of derivative, right? If you know derivatives, then it's kind of easier. So as a result, that's why I wanted to show. So that's an alternative derivation. Alternative derivation of the same thing. Okay. So we know that, for example, the acceleration versus time graph is a constant. Okay. All right. So that's the time axis. So that's the final time. So that's the initial time. So I know that in the velocity versus time graph, right? I mean, this is the derivative of the velocity versus time graph. And the integral is going to give me the velocity, right? Integral. Let me write it down like that, okay? Integral. So as a result, that's basically what I should do. What I do is I basically look at this region in here and then compute this area. okay? So I know that this area in here is equal to the change in the velocity. And by just computing it, I can compute what change in velocity is. So that's basically A times T then. But the change in the velocity is V minus V0. So from here, we get the relationship that velocity has to be V0 plus A times T. Okay. When I'm doing the derivation, I have assumed that A is a positive number so that I can do the geometry in a better way. But the result is still valid when A is negative as well. If A is negative, then the area would be counted as negative and whatever. I mean, let me just stress on this fact, right? There are some situations where we do the derivation, mathematical derivation, by assuming some certain things, by assuming that some certain quantities are positive, for example. But it appears that the result is also valid when the quantities are negative as well, right? In here too, not only the acceleration, but the time also can be negative as well, right? I can use the same result when time is negative too, right? There's no problem with this. I don't need to modify this equation in here. I can use it in the correct way. So depending on whether V0 is negative or positive, or A is positive or negative, I can get a curve like that, or like this, or like that, or like this, all right? I can get any curve actually, but I'm going to assume that I get a curve like that, which corresponds to the fact that V0 is positive, A is positive, but I'm just going to assume this. So let me redraw this again. This is the velocity versus time graph. So it's like that. And that's the time t, that's the time 0, so that's v0. And that's basically the final time in here. All right, let me write this somewhere in here. So let me say it like this. This is the final velocity. So that's the initial one. All right, let me write it down like that, okay? And then we say, well, I'm just going to do the same thing again. I'm going to pass from this to the position versus time graph. And again, I need to evaluate an integral. And that's basically, again, the computation of the area. So this time, this is a trapezoid. Let's say it like this. The area is equal to delta x. I know that. But that's a trapezoid. So in the case of trapezoid, let me show it like this. This is the base length. This is the other base length, right? There are two bases of the trapezoid. And that's the height. And the formula for the trapezoid is basically the arithmetic average of the bases. So that's V0 plus V divided by 2. Multiplied with the height, right? If you want, you can actually think of it as some kind of a rectangle in here, right? This rectangle, right? Where that point is the arithmetic average of V and V0. So it's V plus V0 over 2. And we know that this area is equal to that area. So as a result, I just borrow from that area and add it to there. So the area of the rectangle is the same thing as the area of the trapezoid, right? You can also think of it like this. Yeah, I'm just going to keep this in here, right? So in any case, but from the, let me just say it like this, from the expression of the average velocity, which is delta x divided by delta t, in that case, t, right, delta t, right? But delta t is just t minus t0. T minus the initial time. So it's delta x divided by t. So you can see that the average velocity is equal to the arithmetic average of the two initial and the final velocities. So this appears to be one of the useful relationships. I'm going to explain in a moment, right? in any case, so what we do is, well, we just write this thing down in terms of the initial position and the final position. I know what the final velocity is. That's V0 plus AT times T. And then I arrange everything. So as a result, I get X0 plus V0 times T plus 1/2 of A times T squared. Okay. And so as a result, we get this parabola thing, right? Depending on whether X0 is positive or not, or V0 is positive or not, we may get lots of different shapes in here, but it's a parabola. It is either upright parabola or downright parabola, but it's a parabola. Okay, so basically we just deduce these two relationships, but as I have said before, I mean, you can use calculus for that. Okay, there is a warning in here. Some people, warning, right? The formula is not, the formula is not that one. Okay, so some people just write the formula with a minus sign, or sometimes some people add a minus sign in here, right? These are incorrect, right? Let me actually use a red color to do this. No, that's not a correct one. We have a clear meaning what acceleration is, right? So we have actually deduced this acceleration from the time derivative of the velocity, all right? So as a result, this formula is incorrect, but I know that some people actually, they would like to put the cart in front of the horse or something like that. They just hurry up and then whatever, they just take the wrong value for the acceleration, but put a minus sign in here and things like that. Don't do this, right? No, you cannot put a minus sign when acceleration is negative. So if the acceleration is negative, then you would get an incorrect expression. So if this is negative, then with a negative sign, you would get positive, but normally you should get a negative term in here. All right. So if the acceleration is negative, this term has an overall negative sign. So as a result, this is the correct formula. All right. Let me use a green color. Right. That's still incorrect. Whether the acceleration is negative or positive, whether V0 is negative or positive, this is incorrect, right? Don't confuse this. So you don't change the formula. You need to change the numbers that you insert into the formula, all right? The formula is still the same. Yes, yeah, I know. I mean, there is this idea in here, right? But I mean, let's get the idea correctly, right? We are going to use the same formula all the time. Even in three-dimensional motion, for example, I'm still going to use this formula in here. So the formula is the same, it doesn't change. But the values that we insert in different situations, that's the one that changes, okay? So that's the important warning in here. So next, these are the constant acceleration formulas, right? Let me start with these. So that's the first formula. As the second one. All right. Yeah, let me box them, right? And I'm just going to number them like this. So let me use 1 and 2 in here. So I don't know what that all means, but some people just write the numbers like that. So so that I can distinguish it from other numberings that I use. So here, I'm going to assume X0, V0, and whatever. These are the initial values, and T equals 0. So these are known constants. Let's say known values, right? Let's say I'm treating them as constant, right? So most of the time, in problems, these values are given. And then we have these the position, the final position, final velocity, and the acceleration and the time. So these are my variables. Okay, so just forget about these, the initial values. Let's talk about the final values. Well, I mean, these two are final values. Acceleration is always constant. Yeah, that's the final time too. But we can think of all of them as the final value. So I'm going to think of these as variables. So I have 4 variables and I have 2 equations. So 4 variables and 2 equations, which means, I mean, when I want to write down a formula for, when I want to write down a question for one-dimensional kinematics, then I need to give, first of all, I need to give the initial values. These should be given. That's okay. But after that, among these 4 variables, I need to give 2 of them and ask the value of the other 2, right? Let's express it like this, right? So that means, let me write it down like that, okay? When any 2 is known, the other 2 can be computed. So for example, in the first equation, if the time and the acceleration is known, I can compute x. And for the second equation, if time and acceleration is known, then I can compute v. So as a result, I can use these 2 equations. If a and t are known, then I can compute x and v, right? So I need to give a and t, and then I can compute x and v. You can actually think of it like that. Or you can think of it like this. You can express any one of them in terms of 2 of the others. So as a result, I mean, if, for example, I just think about x expressed as in terms of v and a, there should be an equation that expresses these 3 variables to each other, right? I can also understand it like that, right? So let's say it like this. There is a relation among any 3 of these variables. So as a result, there are actually some formulas where, for example, let's say that in a formula, the time might be missing and the formula relates x, v, and a to each other. In another formula, the acceleration might be missing, so we relate x, v, and t to each other, and things like that, right? So you can see that, for example, in the first formula, let me use a colored thing for this. So in the first formula, there is no mention of velocity in here. So as a result, this formula relates position, time, and acceleration to each other. In the second formula, there is no mention of x. So as a result, this relates the velocity, acceleration, and time to each other. You can actually think of them like that. And so as a result, there should be a formula where there is no acceleration in it. And there is another formula where there is no time in it, right? So let me actually put these 2 boxes in here. So there are these 2 missing formulas in here, right? So there is this third formula and the fourth formula, all right? In one formula, there's some kind of a relationship where the acceleration is missing. And in another one, there's a formula where there's no time in it. Okay, so how can I find this? For example, I can do it like this. So I just use this formula to express A in terms of V, and then insert it in here. And then I get a formula. Okay, I can do it if you want, but it's basically one of the relationships that we have seen before. It's basically the expression for the average velocity, right? Average velocity is, if you remember, the displacement divided by the change in time. And then above, I have said that this is equal to the sum of the initial and the final velocities. All right. I mean, let's just write this thing down like this. But if you think about it, the displacement is x minus x0. So as a result, let me use a yellow color in here. This is a relation that relates the position, time, and velocity to each other. And it's a relationship where there is no acceleration. Acceleration has not been mentioned at all. So as a result, if there is some kind of a particular problem where I don't need to compute the acceleration, for example, I don't know what it is, then I can use this formula, for example. Why not? So in any case, so since we know that the average velocity is delta x divided by delta t, I usually write this thing down in terms of the average velocity. But in any case, it is this formula in here. The last one, yeah, that's the tricky one. Let's see, I think I'm going to use this one in here. So to derive this, that's what I'm going to do. So I'm just going to start with x minus x0. That's equal to, let's see. Yeah, I'm sorry about that. So that's displacement. So that's equal to the average velocity times t. So average velocity was this. Okay. And then I'm going to use t from the second equation. So insert it in here. So that's this. So that's basically the change in the velocity divided by the acceleration. Okay. So what we get in here is v squared minus v0 squared divided by 2a. And I have delta x on the right-hand side. And if I just make things, multiply things appropriately, I'm going to get this expression. Okay. So this is v squared minus v0 squared. That's equal to 2a times delta x. Okay, so there are a few remarks in here. Just a few remarks. The last two equations, do you need them? Well, if you know the first two equations alone, you don't need them. You can actually derive them if you want. No problem with this. As a result, you don't need to know, but it appears that they are useful. And I mean, in some questions, I would be basically asking some particular questions on purpose so that I will force you to use these equations, because it is actually good to be open-minded about these kind of things. So there is the problem of how do you remember them? It's actually quite easy because you would like to express, you would like to understand what they actually mean. This one is easy to understand, right? The third one, it basically says that the average velocity is average velocity. Just remember that this is a kinematic concept. We have defined it as the displacement divided by the time is equal to the arithmetic average of initial and final velocities. Arithmetic velocity is the, average velocity is equal to the, all right. So that's basically what it expresses. So it's quite easy to remember, no problem with this. But there's a danger in here. So some people may assume that this might also be valid for motions where the acceleration is not constant. So let's say it like this. For constant, I mean, this equality is valid for constant accelerations only. Accel only, all right? That's important to remember. So if the acceleration is not a constant, sorry, if the motion is not a constant acceleration motion, then that's not valid. We can give many examples. Like, for example, uniform circular motion. It's a motion where the acceleration is not constant. So you can check later that this is really not the, this is not true, right? Let's see, what else? So the last one, all right, that's not easy to remember at this stage, but later when we see the work concept, we will be basically seeing that this is actually the work kinetic energy theorem. So the left-hand side, if I multiply this with mass, the left-hand side will be the change in the kinetic energy, and the right-hand side will be basically work done by the net force, all right? But at this point, I mean, there's nothing that we can do about this. So later we are going to give a meaning to this. And this is one of the equations that we are going to use later when we solve the dynamics problems. So if you know that the motion is a constant acceleration motion, then you can use this to actually deduce some interesting relationships. But in any case, it's also something that's quite useful to know. So just keep this in mind. Okay. So there's one last thing. And how should I express this last thing? All right. So just remember that these were actually vector quantities to start with, but we said that we are working in one dimension. So as a result, we have to work with the components of the vectors. But let's just remember that these were all vectors. Acceleration, time was not. Time was a scalar. V0, x0, right? And x. These are all vector quantities. And I can continue. Right? In all of these equations, you can see that each term is actually corresponds to, is actually a component of a vector. Right? So as a result, basically, when I do the three-dimensional kinematics, I won't be doing anything. I would be just changing these quantities with the vectors, right? That's the only complication in the three-dimensional kinematics, okay? So all of these quantities are vectors, and as a result, what I'm doing in here is basically multiplication of a vector with a scalar, right? And addition of vectors. We don't have anything else in here. The last equation, however, we have v squared in here. So probably this is a product of two vectors, and it appears like a dot product, right? Here too, this is the dot product of the two vectors. But we are going to see this later when we actually do the three-dimensional kinematics. So it appears that the vector nature is kind of important, at least for the first three equations. Things have to be, these can be actually interpreted as vector equations. The last one is apparently is basically the dot product of vectors. You can actually understand it like that. But this is some kind of an unnecessary extra comment in here. Okay, I don't know if you have any questions in here, but I think I'm going to start solving some problems. Yeah, I have probably solved this problem in the previous semester. So as a result, because I'm using my notes from, I don't know, 20 years ago, 25 years ago, they didn't change, but I mean, there's no modern problems with these one-dimensional motion, obviously. So as a result, I'm just going to write down this question in here. So let's start it like this. So an object, let's say, starts its motion, starts moving towards left. Towards left with initial velocity of 6 meters per second, and acceleration 2 meters per second squared to the right. Right, the expression is kind of important, so that's why I'm spending time in this. So what's the displacement when the object is farthest point on the left, right? I start with the most complicated question. So what is the displacement when the object is farthest to the left, farthest point on the left? Yeah. All right. B, after how many seconds does the object pass from the initial point? All right, I just wrote down the stupid question. So after how many seconds does the object pass from the initial point? I think what is the velocity when C happens? All right, let me just say it like this, okay? So these are the 3 questions. Sorry about this. So in any case, answer, right? I'll start with the answers, but first, no reference frame is given, right? The problem didn't specify in a reference frame, right? It didn't say that the object started from the origin and whatever. So it just describes in terms of left and right, right? So the directions are left and right. So in any case, so therefore this implies that I have to choose my reference frame. Why did I say my? I have to choose mine, you have to choose yours. 15 meters, 9 meters. All right, so we will see. Choose reference frame. Okay, so in any case, so as a result in here, all the directions are expressed with left and right in here. So the velocity is left, acceleration is right. Okay, so there are other things in here that I should mention. So let me add this in here as a note, right? Note velocity is the vector quantity. Right? Speed is the magnitude of velocity. Okay. So as a result, so therefore it's a scalar. So speed is a scalar. Here, all the numbers are also scalars as well, because we are expressing it as a number. But I mean, originally velocity, when we say velocity, it's a vector quantity. So therefore, you have to specify a direction if you want to talk about velocity in here. So let's say it like this: V is the velocity, and S is the speed. That's the relationship, right? Just keep this in mind, right? We're taking the speed as, when we say speed, we always mean the length of the velocity as a vector, right? So it's the magnitude. So it's always a positive quantity. So, I mean, for some reason, the English-speaking people English-speaking scientists actually adopted that convention. And so as a result, we are going to use this convention. So, but we don't have a similar kind of thing for other quantities. So the acceleration, right, position, etc., are vectors. So the position is only a vector if there is an origin, of course. But in any case, so when you are specifying these quantities, you have to also make sure that you specify the direction one way or the other one, right? Usually you need a reference frame for expressing the vector quantities. Sorry, you need a reference frame for expressing the vector quantities. But since there is no reference frame given in here, so we have to use these left and right. So I'm talking about the velocity in here. I'm giving the information about the velocity. So as a result, I give both the magnitude information and the direction information, right? It's towards left. Okay. So these two together actually make up the velocity. And similarly for the acceleration, I give the acceleration by giving its magnitude and its direction as well, right? So without the reference frame, I have to use some directions like that, to the north, upward, downward, or whatever. But with the reference frame, I can use the IJK unit vectors, or if you don't want to use them, of course, you have to use the signs. Okay, so in any case, the first thing in here is to choose a reference frame, right? That's what I'm going to do, right? So I'm then going to choose the origin at the initial point. So that's origin, initial point. And the x-axis pointing to the right. So let's say it like this, to the right. So that's the positive x-axis. In that case, sorry about that, I don't have space in here. So that essentially means, yeah, let me start with this, right? First, initial position is equal to 0. So I can then decide on this. Initial velocity was towards right, and the acceleration was towards left. So therefore, I can also decide on what these things are. So the problem only specified its magnitude, but now I can specify its sign as well. So in that case, the acceleration would be negative and the velocity would be positive. But just keep in mind that I can only decide on this after choosing the reference frame. Okay, so in any case, the initial velocity was 6 and whatever. This is 6 and 2, so therefore this is 6 meters per second, and that's minus 2 meters per second squared. Okay. I could have solved the problem like this. Yeah, I'm going to solve the problem with the other choice of the reference frame, but let's just first solve the problem like this. I think, I mean, what does that mean? Let's just try to express it like this. I mean, the velocity is to the right, but the acceleration is to the left. It actually means this. So if the velocity is like that, initially like this, then the change in the velocity, delta v, which is acceleration times delta t, this is always pointing towards left for positive times, right? That's essentially what it means. So that means that at a later time, the velocity would be a vector which is pointing perhaps towards right, but the difference between them, delta v, would be pointing towards left, right? Okay, so that essentially means that the velocity changes in the leftward direction along the direction of the acceleration. So as a result, later the velocity will become like that, and later it will become like this. At some point, it will become 0. Sorry, I just confused my left and right. Sorry about that. Somebody warned me? No. So an object starts moving towards left. Yeah, sorry about this. I confused left and right. All right, let's just give a break, and after the break, I'll correct this. All right. So in any case, so initial velocity is towards left. Sorry. All right, let's just draw this again. But initial velocity is towards the left. I don't know which problem I'm solving. And so initial velocity is -6 meters per second, but the acceleration is towards right. And so therefore, this equation does not have any meaning. Okay. Yeah, it was easy to correct. All right, so I'm going to solve with this, but the previous comments would be valid. So the velocity always changes in the rightward direction, and that's the meaning of that. Okay. All right, so let's give a break in here.